Hi, I'm Yinkai, and I'd like to share with you my work on avoiding coherent errors with rotated concatenated stabilizer codes. So the type of errors I'd like to focus on today are coherent phase errors. And coherent phase errors are unitary matrices that are generated from this matrix over here, which is a sum of Pauli's, which are diagonal Pauli's that occur on individual qubits. For example, this is a Pauli zeta x on the first qubit, and it's a Pauli zeta x on the nth qubit. And these coherent errors can arise from a multitude of reasons. For instance, because of stray fields that interact with your system of identical qubits, or you could have a collective drift in the energy levels of your physical system. And moreover, if you have a physical system that comprises of identical qubits over here, your Hamiltonian will be proportional to this matrix over here, and the unitary evolution on the system will be of the form of a coherent of this U matrix over here. And if your system is not in an eigenstate of this U matrix, you will need to uncompute this U matrix. However, you may not be able to know the value of theta, which is the energy level of your physical system with an infinite level of precision. And therefore, even when you do the unrotation, you would have some residual coherent phase error. These coherent phase errors are much more damaging than stochastic errors. And because of this, there's a lot of recent work that has focused on addressing coherent phase errors in physical systems. And there are a number of approaches to combat these coherent phase errors. Of course, one could use a quantum error correction code, and this is exactly what I will talk about today. However, there is more that we can do aside from just using a quantum error correction code. One can use quantum control techniques where one applies like the dynamical decoupling sequences to try to remove the noise as it occurs. However, the problem with quantum control is that it can be very challenging to implement, and also it requires resources, and these resources can be potentially expensive. And moreover, quantum control itself could introduce some additional noise into the system. And so there's an alternative way to avoid, to combat errors, which is to completely avoid the errors. And errors can be completely avoided if the action of the said noise operator does nothing to the quantum code that you use. And these codes that have this property are known as error avoiding codes, or codes that lie in some decoherence-free subspace. These error avoiding codes have been studied over 2 decades ago. However, there hasn't been a lot of recent follow-up work on this. However, the field of quantum error correcting codes is a very mature and has a very well-developed theory for fault tolerance. And this brings the question, well, it's really nice to have error avoiding codes because you can completely avoid, say, coherent phase errors. But what about fault tolerance? Can we integrate quantum error correction codes with some nice fault tolerant structures with these error avoiding quantum codes that may not have a very nice fault tolerant architecture? And the answer to this is I will give you it in a bit. But first of all, I'll talk about what codes can completely avoid these coherent phase errors. These codes are codes that are comprised of constant excitation states. These constant excitation states are just superpositions of computational basis states where the weight of these binary bit strings is a constant. For instance, if you have 2 qubits, you could have a constant excitation state with excitation number of 1. In this case, you can see you just have code words with Hamming weight of 1, and you can have superpositions of code words with Hamming weight of 1. And these are constant excitation states. And the constant excitation states I'll focus my attention on are these really trivial looking constant excitation states on 2 qubits. The first is a 0 on the first qubit and a 1 on the second qubit. I'll call this the logical 1. And the second is a 1 on the first qubit and a 0 on the second qubit. As you can see, these are constant excitation states on 2 qubits where the excitation number is 1. There's only 1, 1. And these states were studied by Neil Laflamme and Milburn, but not in the context of quantum error correction. And hence, it is unsurprising that these, if you look at these logical code words and you think of them as a quantum code, they correct no errors. The distance is 1. But this is not a problem because we can apply code concatenation. You see, this is the encoding circuit of a Neil Laflamme-Milburn code. And if you have a stabilizer code over here, then you can write this encoding circuit in this very general form over here. The concatenated constant excitation code that we propose one can use would be just the concatenation of the stabilizer code with this Neil Laflamme-Milburn code. And there are many ways to look at this concatenation structure. Of course, it is the concatenation of a stabilizer code with something that's a non-stabilizer code, a Neil Laflamme-Milburn code. However, you can also think about this concatenated code as the following. First, you concatenate a stabilizer code over here with a bunch of length 2 repetition codes over here. And after you have this concatenated code with a repetition code, you apply these rotations, these Pauli rotations over here. And because the codes that I propose have this structure, I call them rotated concatenated stabilizer codes because they are rotated from this concatenated stabilizer code. And I denote such a code like this, which emphasizes that it's the concatenation of a stabilizer code with a Neil Laflamme-Milburn code. And the nice thing about these codes is that they inherit the logical computations from the underlying stabilizer codes. You see, if you have an m-qubit stabilizer, m-qubit logical operation on a stabilizer code, and you want to find the logical corresponding logical computation on this constant excitation code, one could follow this 2-step procedure. First, find the logical operation on the stabilizer code concatenated with the repetition code and call this operator this. It is clear that this operation is easy to find because it's a stabilizer code. Next, find the corresponding logical computation on the constant excitation code. And for this, one just needs to do these rotation operators, sandwich this logical operation over here with these R's over here, and one can get the logical computation on the constant excitation code. So yes, we can inherit a whole load of logical computations from the stabilizer formalism. Now, what about syndrome extraction? What if there are errors that occur on the constant excitation code, like some local stochastic errors? Can we also correct them in the same way using stabilizer code formalism, even though this constant excitation code is not a stabilizer code? You see, this constant excitation code is not a stabilizer code because when you have these stabilizers and you act on them, the eigenvalues of the stabilizers are not all one. So it's not a stabilizer code. However, it lies in an error coset of the stabilizer code because the rotation that brings the constant excitation code out of the stabilizer code is itself a Pauli error. And because of that, and because the constant excitation code lies in an error coset of the stabilizer code, one can just use the stabilizer formalism to extract the syndromes. And with just a mild modification to the coding algorithm, one can apply error correction on the constant excitation codes. So this is great, but what about fault tolerance? Now, if one restricts the underlying stabilizer code to be a fault tolerant stabilizer code, say this fault tolerant Steen code. So in the fault tolerant Steen code, one can concatenate the Steen code multiple times and prove that it has a fault-tolerant threshold. And this was done more than a decade ago by Aliferis, Gottesman, and Prescott, using the technique of extended rectangles, where basically basic operations that one would want to do on the quantum code, for example, like logical computations, state preparation, would be padded by these error correction circuits. And in their proof strategy for evaluating bounds on the fault-tolerant threshold of this concatenated code, all that was needed to be done was to count the number of ways this extended rectangle could go wrong when you put a finite number of, when you put a bounded number of faults within each of these extended rectangles. And essentially, the core of the result is, as long as these extended rectangles have a finite number of circuit elements, then there will always be a finite threshold. And because we have, we can show this, and hence these constant excitation codes we have will have corresponding extended rectangles that have a finite size. And this would lead them to have a positive fault-tolerant threshold. And we can also look at constant excitation codes for amplitude damping codes. For if one is interested in amplitude damping noise, one can take, for example, the 4-qubit amplitude damping code by Leung, Nielsen, Chuang, and Yamamoto, and concatenate it with the Newell-Laflamme-Milburn code to get this 8-qubit code that can correct one amplitude damping error. And it essentially inherits its amplitude damping error correction capability from this Leung, Nielsen, Chuang, Yamamoto code. And then you can see there are many ways one can get to this code in this table over here, but I won't elaborate too much on that. And what I want to emphasize is that because this construction, this concatenation construction is so simple, one can easily construct, for example, encoding circuits and also computation circuits for these for this specific 8-qubit code for amplitude damping errors. And one can also have a very nice decoding circuit for this amplitude damping code, which uses a lot of ideas from stabilizer codes because it is very closely related to stabilizer codes. But the key message I would like to bring home today is that there is a huge advantage in using these constant excitation codes if the noise model is dominated by coherent phase errors. So now let us consider a noise model where with some probability there will be some coherent phase errors, and with some probability there will be some stochastic errors. Now let us consider the scenario where stochastic errors are rare. For example, if stochastic errors occur with probability like 10 to the -9, in that case, this plot I have over here shows that if you want to have a target level of infidelity for the quantum code, for constant excitation codes, you can just use the Newell-Laflamme code and you have no errors, essentially no errors. However, if you did not avoid the coherent phase errors, one would need to correct, for example, over 30 qubits, and this y-axis over here is the number of errors you need to correct. The more errors you need to correct, the larger the quantum code you need to use, and the more hopeless it is to perform it on near-term quantum computers. So the message is that as long as the noise model is dominated by coherent phase errors, you can reduce the number of qubits you need to correct by a huge amount. So instead of correcting 30 errors, all you need to do is correct, well, at most 5 errors. And because of this, you can use codes that are very short. Instead of using like hundreds and thousands of qubits, you can maybe use just at most a few hundred, or maybe even less than 100 qubits. And so this is a table that compares our constant excitation code with some other codes. So this constant excitation codes have been previously studied, these error avoiding codes. However, previously these explicit circuits have not been presented, and they do not also correct arbitrary errors. And while other constant excitation code can correct some other errors, they don't have these very nice circuits. And basically, the concatenated codes that we introduce here solve all of these problems. They avoid coherent errors, they have explicit circuits, and they can correct errors. And so for future work, we think it will be very useful to conduct some explicit numerical analysis on the fault-tolerant thresholds, because over here, we just proved that we can't have a positive fault-tolerant threshold. But then one would like to know what number the fault-tolerant threshold is for practical scenarios. And also, it will be interesting to see what applications these constant excitation codes can have in quantum metrology and also in quantum simulation. And I thank you for your time for listening to me today.